Okay, so let's talk about it. Doctor's mistake, confusion of the inverse. Let's assume that about 1% of the population has a form of cancer. We'll just assume that. It's probably a little high, but let's just say so. 1% of the population has a form of cancer. That is, if we select a person at random, the probability they have cancer is 0.10. Oh, wait a minute. That's not 1%. There's already a mistake on the handout. 0.01. I typed it up late last night, and it's got a mistake. Change that to 0.01. There's the first. Hopefully, maybe the last. We'll see. Yeah, it's 0.01. So the probability that they have cancer is 0.01. Next, let's also assume that false positive rate. The false positive rate is 10%. That is, the probability of a positive test result, given the cancer is not present, is 10%. That's called a false positive. Remember, all medical tests, no medical tests are perfect. They just aren't. They give false, that you could really have the disease, and they say no, or you don't have the disease, and the test says you do. Sometimes, right? No medical tests are perfect. And that means we need to use statistics, doctors do, to figure out what's really going on in a patient. The body's complex, things aren't very simple, statistics get involved. So, again, false positive rate is 10%, meaning the probability that you'll get a positive test result when you don't even have cancer is 10%. So you go in, you were given that cancer is not present. You really don't have the cancer. They give you the test and it says positive, you got it. The doctor says that test came back positive. Looks like you have cancer. Turns out you don't. That happens 10% of the time. Now, is that real? I don't know what the number is, but there is some number. False positive. False positive. Next question. Let's further assume that the true positive rate is 80%. So that means you'll get a positive test result given that you really do have cancer. So if you really do have cancer, you go in there and you've got cancer, the test will tell you positive. Yes, you really have it, which it should tell you that, right? Only 80% of the time. That means 20% of the time it doesn't say that. All right. Given all of these assumptions, let's consider this question. If someone goes to the doctor and tests positive for cancer, say you go to the doc, and he or she gives you a test for cancer, and it comes out positive, saying you have cancer. What is the probability that you actually have the cancer? That is, what is the probability of cancer given a positive test result? What's the probability of cancer given a positive test result? And here comes the interesting fact. When 100, this is true, I'm not making this up at all. This is famously known about this question. When 100 physicians, doctors, medical doctors, were given the above information, this exact information I just gave you, 95 of them, 95 out of 100, 95% per 100, estimated the probability that someone has the cancer, given that they get the positive test, to be around 70% to 80%. And they were wrong. Way wrong. By a factor of about 10. Their answer's 10 times too high. They are miles off. They are not understanding the probabilities involved. And I want you to understand the probabilities involved. So why not? Well, first off, why is that answer so wrong? Here's something that you might think right away. It would be natural to think this. I did. I got tricked on this the other day. I was at a math party thing, and somebody asked me, and I just answered off the cuff, and the person's like, "No, you're doing that." I'm like, "Oh yeah, that's right." So it's easy to mess it up. Meaning this, you read this right here. The person just said it verbally to me. You read this right here, and you think, positive test result, given that you've got cancer. Isn't that what they're saying here? Right? Isn't that exactly what's being said here? If someone goes to the doctor, tests positive for cancer, what's the chance that you really have it? Well, it's that. That's it right there, isn't it? Test result given that you've got cancer. 80%. And that's wrong. And that's what the physicians did. That's why they thought the answer was somewhere between 70% and 80%. They were looking at that 80% going, yeah, it's about 80%. It's about like that. No. Why is that wrong, first off? Why isn't that exactly the same thing? See how that's a switching of the order of the given? That's what I didn't carefully listen to when the person asked me the question. It's a switching of the order. And that really matters. Let's see, what are we talking about? Well, right up here, this 80%, this is positive result given cancer, right? But down here, the question is cancer given positive. That's different order. See how that's a swapping of the order? And that's not small. That's huge. That's a very different question. But many, probably most, I'm sure the majority of society doesn't realize it. And even the physicians switch it around and don't realize that's actually a very different probabilistic question. All right, so why so? How do you actually do it then? What's the right answer? All right, let's go forward. So taking this table. So to make things easier, let's assume, here we go. So let's fill in this table as we go. To make things easier, let's assume a population of 1,000 total people. Where do you put the 1,000? Lower right corner, right? That's the total. Let's just lay out some numbers nicely. So fill this in as we're going. So put the 1,000 down there. We good? All right. Next, recall that so I'm just saying, hey, let's take a group of 1,000 people. Just to make it simple. Let's just take a nice clean number. Let's suppose we have 1,000 people. All right? 1% of the population has cancer, right? Isn't that what they said back here? Back in the beginning? 1%, even though I did the wrong thing here. 1% of the population has cancer. That was the first assumption. There were 3 assumptions, right? So 1% has cancer. Calculate 1% of 1,000 people. How do you do that? How do you calculate 1% of 1,000? 0.01. What is of always? Times 1,000. So it's 0.01. You just make a decimal and you multiply by 1,000. And you get 10 people, right? 10 people is 1% of 1,000. Right? If you take 10 100 times, you get 1,000. Right? That's 1% of 1,000. Now, put that in the table in the correct spot. Hint, it is a total. So if 10 total out of the 1,000 in our population have cancer, where's the 10 going to go? Yeah, right there, huh? Does that make sense? Because that's the cancer total, isn't it? Is that good? 10 people total have cancer.
So that's regardless of them testing negative, right?
What's that?
That'd be regardless if they test negative.
Yeah, we don't know how they tested yet. That's just 10 total people. Well said, well said. 10 total people that have cancer. We don't know what the test said, but we know they really have cancer. Exactly. Now, next, if 1,000 is our total population and 10 have cancer, how many do not have cancer? Out of 1,000 people, if 10 have cancer, how many don't? Just subtract them, huh? 1,000 minus 10, 990. Put that in the correct spot. Where's the 990 going to go? That's going to be right there. That's going to be the no cancer, isn't it? Again, we don't know if those people tested positive, tested negative. We don't know anything about their test. We just know they don't have cancer. All right, let's keep moving. So now the second assumption. If you go back, it said positive test result given that cancer is not present, 10%. This means that among those who do not have cancer, right, given that cancer is not present, those that don't have cancer, 10% of them got a positive test result. It said they did when they don't. Calculate 10% of 990. How do you do that? 0.10, yeah, times 990, right? Of is times again. It's 99 people. Put that number in the correct spot in the table. So that's 99 people who got a positive test result even though they don't have cancer. 99 people got a positive test result even though they don't have cancer. That would be right there, huh? No cancer, positive test result. Making sense? Next, it says, after calculating, can you finish calculating the one empty cell in the no cancer row by subtraction? Can we get this? Right? If the no cancer, if 99 people are here, what is here to make 990 total? It's got to subtract them, huh? Right? We good? So we go 990 minus, what is it, 99? 891? Is that what it is? 891 must go here. That must mean there was 891 people who got a negative test result and had no cancer, because we know there was 99 that got a positive test result and had no cancer. That must mean that, right? Keep going. Now, final assumption, number 3. Positive test result given that cancer is present, 80%. This means that among those who have cancer, really have it, 80% got a positive result. Calculate 80% of 10. So that's 0.80 times 10, which is just 8. 80% of 10 is just 8. Put that number in the table in the right spot. So where's that 8 going to go? They got a positive test result and they have cancer. Positive test result and they have cancer. Upper left, huh? Those 8. And if that's 8, 8 plus what is 10?
2.
It's got to be 2 here because we already know the total's 10, which is the part they're saying here by subtraction, right? 10 minus 8 is 2. Do that. Finish. Now, finish adding vertically to get the bottom 2 total cells. So, let's add these up. 8 plus 9 to get the total. What's that going to be? 107. And add these up. 893. To get the total. Now we've got the whole table. Now we're ready to answer the question. What's the probability of cancer given a positive test result? Cancer given a positive test result. How many people were given a positive test result? It's the total number in the table. How many got a positive test result? 107 got a positive test result. Whether they had cancer or not, they got a positive test result. So it's 107. Out of these people, how many actually had cancer? Out of these 107 people that got a positive test result, how many actually had cancer? Only 8. 8. And then that's our, if you read these words, it basically says 8 divided by 107, right? That's the chance of getting of cancer given you had a positive test result. Right? 107 people got a positive test result. Out of all those, how many actually had cancer? 8. So the chance of you actually having cancer, if you get a positive test result, is 8 out of 107. So 8 divided by 107 on your calculator, I'm getting 0.0748. And there's the actual answer. If you read those other words, remember, they estimated 80%. In reality, it's only a 7% chance. If you get a positive test result, you only have a 7% chance of actually having cancer. So different than the 80 and the confusion of the inverse.